Speaker. The speaker is Salmin Sultana. She's a senior PhD student in the electrical and computer engineering here at Purdue University. So she does research on the area of provenance in sensor networks and in distributed computing systems. So I leave the floor to Salmin.
Hello everyone. So I think Professor Bertino has just introduced me. Then I'll just go directly to the presentation. So can everyone hear me? Okay. So today I'll just talk about our research on secure provenance transmission for data streams. So now I'll just go directly to the presentation, and if you have any question in any of the time of the presentation, you can just stop me and ask me. So provenance is actually a very familiar name in the art and literature, where forgery is very common, like some piece of work is just done fraud by some persons, and this fraud piece of work is just sold to some party. So in this way there are forgery that was happened earlier, and now it is also been happening. So to prevent this kind of forgery, so what is done in this area, so the ownership history of the piece of work is recorded in a secure way, so that everyone can just check the integrity of the information before doing any kind of like buying or any processing with this piece of art. So this thing, the history of ownership of a piece of work, is known as the data provenance. So this is just for some physical object, but what about the applicability of this data provenance in digital world? Just to illustrate this concept in digital world, I will just consider here an example with enterprise network. So as you just know, there are like so many users, and who can just transmit to some other party using several routers, and there are also servers, and each user can also like run many applications. So now just consider an example where this user here, this application here, just transmits some data, and it gets routed through this path. But at any point, maybe say at any router, there may be some kind of data aggregation. So there is like some value change to the value. Maybe in another point there may be data alteration. It may be due to say, some intended purpose like data truncation or this kind of stuff, or maybe some malicious attack. There was some attacker who just changed the data value for its own intention. So now when the data just gets routed to the internet and receives to its intended receiver, the receiver has actually no way to know whether the data was changed from its original value, or it was changed for intended or malicious purpose. So thus it's actually a very important issue to trace the path of this electronic data, or like the processing steps of the data, so that the receiver can know whether there was any change or whether it was malicious or not. So thus the provenance in transmission and provenance processing is a key problem in the field of information security. Now I will just talk about some use cases of provenance for say various security functions or any other purposes. So the first thing I will talk about, like data exfiltration, how provenance can help to exfiltrate sensitive data from an enterprise towards the outside of the enterprise. So in this case, like whenever an application or a user generates some data, it will also associate the data provenance along with it. So what may be the provenance for this data? It may be some like secure tagging. So it will be used to mark some sensitive file or information, so that you can just check whether this information is sensitive or not using that tagging. So whenever like one application will just send some data that contains any part of this sensitive file or any part of the sensitive object, it can use that tagging as a provenance information to that data. Now this provenance will traverse along with the data towards the router that will decide whether the data will go outside or not. So in this case, this router will check the data packet for any secure tag that is attached to it as a provenance, and then if it finds any kind of secure tag, it will decide, okay, I will not just transmit this sensitive data outside the network. So in this way, provenance can help to apply these data access control policies, and also just to ensure the data exfiltration properly. Now we can also like talk about any other application like intrusion detection. So the provenance can also help to check whether there was any malware or any denial of service attack. So now just think that here in this server, there was some malicious party that just transmitted some fake data, but the underlying system will also append the provenance along with the data. So in this case, what may be the provenance? You can just include all of the applications that processed or modified the data as the provenance information. And now when this data along with this provenance goes to the decision making entity, it will check whether all of the history of the originating application, and check whether this signature or this pattern matches with some known malware. Then it can also decide that the intrusion anywhere in the network. So these are just two simple use cases of provenance. Just to summarize the provenance storing and provenance transmission, and also the use of provenance, I just show here a compact picture that says a secure provenance life cycle. So at the lower layer, you see that these are the physical entities that will generate some data and also transmit this data to some authority. But along with the data, it will also attach the provenance in a way that ensures secure provenance transmission. Now when this data goes to some application or some authority, it can be used to ensure some security service like data exfiltration, as we said earlier, or maybe detect whether there was any packet drop or not, or also assess data trustworthiness. And now at the upper layer, there are several applications that we see in our like system or any enterprise application. So these application can use any of these security functions to just ensure their security properties of their application. So this is just the summary of the whole provenance cycle. So now what is our problem we are considering here? So the problem we are working with, like how to securely and efficiently transmit provenance along with the data for data streaming environment. And for this presentation, I just consider the focus on the sensor networks. Okay, so do you have any kind of questions or anything I can just clarify? Okay. Okay. Okay, so now we have to think what are the ways to transmit provenance, like. So just as a naive way, maybe just to transmit the provenance along with the data as a plain text, but as intuitive, it will be highly vulnerable to attacks, like, because there is no assurance of integrity or confidentiality. Now what about the traditional security mechanism like cryptography? So in this way, the provenance will be encrypted along with the data and transmitted. But what is the problem here? There will be high computational cost here, and if one data packet is dropped, there is no way to recover or like know about the provenance of this data. So what about the watermarking? I think this is, just to let everyone know about the watermarking. Watermarking is a mechanism that is used to hide some information within a carrier, like within a data you just hide some information. So this is known as watermarking. So in this case, what we do, we will just like the embed the provenance along with data, so that at the end this is just the data with provenance. But the advantage here is that the provenance is almost invisible, so the attacker cannot distinguish the data with the provenance. And also, if there is some information lost, if a good watermarking scheme can recover the information and also recover the provenance, and there is also less power and processing requirements. So, we adopt watermarking as a mechanism to transmit provenance in sensor networks, but what are the challenges here? Like we said that maybe we can use data, sensor data as a carrier to embed provenance, but the scheme should be actually be the provenance solution should be scalable enough so that it can handle any large sensor networks, and also the watermarking mechanism should not degrade the sensor data values significantly. And also if the solution would also be adaptable to process the fast or real time data, and it should make a compact representation of the provenance that is supposed to transmit with the data. So these are all the challenges here, and based on these requirements and challenge analysis, we have come up with a solution that embeds or watermark provenance over the interpacket delays. That is, we do not use data values as a medium for embedding provenance, rather than the timing difference between each data packet that is transmitted by the sensors are used to carry the provenance information. So these are just like some system specific assumptions here. So we consider a large sensor network where the sensor nodes will be static after deployment, but as we know that there may be some resource optimization or power failure in sensor networks which may change the routing paths frequently. And after the deployment, the base station will assign each sensor node a secret key, a unique pseudo-noise sequence that is of LP bits. So I will just talk about this PN sequence later on. And also there may be multiple data flows that is generated from various sensor nodes, and the source will generate periodic data. And after generation, I mean before transmitting the data, the source will timestamp the packet with its generation time. Now what about the provenance? So as we saw the examples there, we included different things as provenance metadata. As provenance is actually used in like various domains, the definition of provenance actually depends on the application of this provenance or the domain of provenance. So in sensor network domain, we use provenance, we define provenance as the information about the source node and the routing nodes that the data packet traversed to reach the base station. So here we just see two pictures, like in the first picture we see the data is generated by node N1 and it follows this path to go to the base station. So this path information is known, this is the simple provenance. And here in this picture we see that there is some aggregation happened in this node. So there we will use all of this node information in the provenance. So this is called aggregated provenance. And what about the adversary security assumptions? We assume that the base station is powerful enough and it cannot be compromised, but there may be also maybe the source nodes will be honest, but there may be some intermediate nodes in the path that get compromised, and they can drop, inject or alter data packets on the links under its control. So now I will just pictorially describe the high level overview of our provenance watermarking mechanism. So this is just a simple, very simple network here, and these nodes with circles and numbers in it are the sensor nodes with node IDs, and this A1, A2, these rectangular boxes, those are also sensor nodes, but I just say this we can distinguish it from the normal nodes because these are aggregator nodes where the data get aggregated from the children values, data values. Here we consider N1 as the source node, and this path with the red arrows, this is the data traversal path. So as we see that the provenance information will be transmitted over the interpacket delays. So for the first packet that is transmitted by the sensor node 1, sensor node 1, it will not experience any delay. So whenever it is generated, it will be just transmitted towards the base station. And whenever a packet reaches the base station will record its arrival time. Now what about the next data packet generated by the node 1? So we are supposed to embed provenance between over the delay between packet 1 and packet 2. So for this case, after generating the packet 2, we will not transmit it instantly. Rather than we will generate actually some delay value based on the provenance information, and then delay the packet transmission by this time. Like now we see here the generation time is like 26 second, but we will also delay the transmission by this 50 milliseconds. So now the sending time would be this time. So there is some delay in the transmission. Now at each node, when the node goes to the next intermediate node, each node will embed its provenance information. That means each node will generate some delay based on its provenance information and delay also the transmission of this packet. And the same thing will be repeated at each intermediate node. And whenever finally the packet reaches at the base station will record its arrival time, and by the difference between the arrival time of packet 1 and 2, it will record this interpacket delay value here. Okay. So now what is this interpacket delay means? This interpacket delay is due to like generation time delay, like after 10 seconds of generating the packet 1, packet 2 was generated. But also here are some other delays that was introduced due to the provenance embedding, right. So now this IPD also contains the provenance based delays. And this same thing will happen for some other packets, and after this we here just consider 5 packet transmissions and we get 4 IPD values here. So just it will be clear here that the provenance transmission requires a number of packet transmissions here, and based on this number of IPDs, the base station will retrieve the provenance of this data. And we will there is an assumption here that like we say that the provenance is actually for some data object, but here there are like 5 data objects, but we just send one information here just bit by bit. So the assumption here is that for all of these data packets the provenance will be the same, and this requires actually the routing path will be the same, and our assumption was that like for some time the routing path will be the same, and afterwards it may change, but for it, if it is a stable network, for some time the routing path will be the same. Okay. Now I will just go into a bit more details of the mechanism. So the provenance watermarking is actually happened at each node in the routing path. And what is the provenance information that is now embedded over the interpacket delays? This is the PN sequence that was assigned to each node, and this is a secret thing. And since the PN sequence acts as the provenance information and its length is LP bits, so the provenance transmission will actually require the LP plus 1 packet transmissions. And over each, at each packet, over each interpacket delay, there will be only 1 bit of provenance information embedded, and this embedding, this 1 bit of provenance watermarking requires 3 steps, that is generation of delay perturbations, the delay that will be added to the interpacket delay, and the selection of a delay perturbation which delay will be added to the interpacket delay, and then provenance watermarking, how this provenance information is watermarked through that delay. So I will actually go into more details of these steps. The first step is generation of delay perturbations. So as we said that there will be LP plus 1 packet transmissions required for provenance transmission. So there will be like LP IPDs, and for each IPD the node will require 1 delay perturbation. So how this is generates? So each node Ni actually uses its own PN sequence, that is its provenance information, and also a locally generated impact factor alpha I that is actually generated at each node. This is not known to base station or any other node, but the base station may know the distribution of these alpha I's. So using this PN sequence and also this impact factor, each node will actually generate a set of delay perturbations, that is just some scalar the scalar value alpha I multiplied with the vector p and I. So then it will generate a set of like LP of real values. So those are the set of delay perturbations used for provenance embedding. So see here, the set of delay perturbations actually depends on the p n sequence that is fixed, and alpha I that may just change, or but it follows a distribution. So this generation of delay perturbations may be offline because it does not anyhow depend on the packet specific information. So this may be offline or just upon arrival of each packet. Now the next point is how the delay perturbation will be selected for each IPD or for a packet. So whenever a node gets a packet from a data flow, like it is the j+1th packet in a data flow, so it records the interpacket delay, that is this here denoted by this delta j. And for this delay perturbation, it will actually have to select a for this IPD, sorry, it will have to select a delay perturbation from the set of delays that is new here that was generated earlier. So how this selection actually occurs? So here we use this hash function. I just will not explain this, but I will say this hash function mod this LP actually generates an index from 0 to LP minus 1, and that index is actually used to get a delay perturbation from this set. So now it will generate an index, and based on this index I will just get a delay value from here. And just for the ease of explanation, I will just denote it as Sij. And now later on, the next step is how does the provenance embedding is done, what is the provenance watermarking. So we have one IPD and the delay perturbation selected for it. Now what I will do, I will just increase this IPD by this delay time, like I will delay the transmission of this packet at a node by this Sij time unit. So see, the Sij, the computation of this Vi here depends on the PNI, that is the provenance information. So this Sij actually corresponds to a provenance bit, and now if we just now we delay the transmission, in this way the provenance information is actually watermarked over the IPD. So in this way, actually through these steps, the provenance information, one bit of provenance information is watermarked at each node, and this will be done at all of the nodes in the intermediate in the routing path. So at the end, the interpacket delay at the base station recorded at the base station will actually contain one bit of provenance information for all of the nodes in the routing path. And this procedure will happen for each packet, and at the end of the LP plus 1 packets, the base station will have the set of IPDs. From that it will be able to retrieve the provenance information. So now the provenance retrieval things. So it is happened at the base station. Now the base station actually say doesn't know which nodes embedded the provenance information, right? So it may not know the routing path or anything else. So for this thing, it will check for each of the node in the network whether this node is included in the provenance or not. So this then how these things happen at the base station. So there are two steps here. So the first one is the base station record the IPD, and it will reorder the IPDs for each node, and then will check based on a threshold decoding step. So I will just describe it here. The first thing is the base station now has a set of IPDs. So what does it do? So for each node, what the base station do, it just reorder the IPDs using the selection algorithm. Like the base station has the PN sequence for a node and also the say impact factor. So it will then do the selection algorithm for each of the IPDs, and then generate a permutation of the IPDs that is specific to each node. So I just denote it here by CSI. So then it has generated the sequence of IPDs, and what it will do with this sequence, then it will compute the cross correlation between this sequence and the PN sequence of that node, and this cross correlation value will be like compared to some threshold. This threshold is just determined offline at the base station. So, if the cross correlation value is greater than this threshold, then the base station decides that okay, this node embedded its provenance information. So, in this way the base station will do this mechanism for each of the node in the network, and for those nodes that it gets this cross correlation greater than T star, it will decide okay, these are the set of nodes that was actually in the routing path and embedded their provenance information. So, here this is the whole mechanism of provenance embedding and retrieval. Now, what are the security features that this scheme provides us? So, this is actually listed here like confidentiality, integrity, freshness and unforgeability, but how? See, the PN sequence that is used as provenance information, that is secret to each node, and also it uses the secret key Ki. So, thus the provenance embedding actually requires some secret informations for that is just specific to each node. So, if one node embeds this provenance information, there is no other way for other nodes to retrieve this information. So, this way the mechanism ensures the confidentiality of the provenance. Now, what about the integrity, like to change the provenance information? Obviously, it can be done that you will just mess up the whole thing and it will just say it will be some just garbage value. You can do this, but that is not some intelligent way to do some kind of attack. Say the attacker may want to just change the provenance information to include some other legitimate node, like node 1 just embedded its provenance information, but the attacker wants to know okay, I will just remove this node 1 and include some other node like node 3. So, is that possible here? Because like to embed provenance for a node, it requires some secret information. So, the attacker will not know those information unless it just compromise some node, right? So, in this way the integrity is also assured here. What about the freshness? Freshness means you cannot like capture some old provenance information that was, say maybe there may be in the network there may be some malicious node that just observes the data packet transmissions, and then it will just capture some old information and say for later packets it will say okay, this is just the provenance for this information. So, is this possible here? But say the provenance embedding actually requires the packet timestamp. So, the timestamp actually changes for each packet, right? So, in this way also we can the attacker cannot just attach some old provenance information to a data packet. And also the unforgeability, that is just you don't can do the like forging or integrity breach thing here. So, now I will just see some show some experimental results here. So, the main objective of the solution was, as we talked about the challenges, like it should be scalable to handle with the large networks. So, how the scalability can be hampered here? Since we just use the interpacket delays for provenance embedding, so it may happen that the time that takes to reach the base station is quite large, so that there is no use of the data at the base station. So, that is why we here measure the time that it takes that is added due to our provenance embedding thing. But we say that like the data is generated like every 5 minutes here, but we conduct the experiments for different length of paths. Maybe the path length may vary from 2 to 8, 10 here, and we see that actually the watermarked interpacket delay increases from the normal interpacket delay by a maximum of 6%. That means up to this 12 length paths, which is which is actually usual in normal sensor networks, the IPD increasing is not that much, that is beyond the tolerable range. So, in this way our solution means scalable to some large networks. And what about the resiliency to attacks? We also said that it should be able to recover provenance from various if there are some attacks here. So here we actually consider several attacks like insertion attack or deletion attack or alteration attack. So what is this? The insertion attack means that okay, so the provenance is actually preserved over the interpacket delays. So why not some attacker will just increase alter this delay somehow, like it will also inject some false packets here so that the interpacket delays don't get preserved here. But we through experiments and also our checking mechanism at the base stations, we showed that okay, so the it is almost possible to recover the natural desired data, desired provenance from the insertion attacks, and the base station can detect the injected false packets and thus remove those, and then it can also easily retrieve the actual interpacket delays. And in this way, for various percentage of inserted packets, we see that the decoding error is actually less than 0.2, 0.3%. And what about the deletion attack? It means that the attacker will just drop some packets. So what if the attacker will just drops packets, and in this way the interpacket delays will not preserve the embedded provenance delays. So to this is actually really a problem, because this is not like insertion attack that we just discard the fake packets and just get the actual IPDs. So for this case, we actually what we did, we recorded the IPDs multiple times and then used an averaged, weighted provenance mechanism, weighted voting kind of things, and this way we saw that we can recover the provenance information against this attack. So here we see some kind of redundancy factor. This actually means how many times we recorded the IPDs, the base station recorded the IPDs, and then took their weighted votings. And we also see that okay, up to certain extent we can tolerate the deletion attacks. So there are also another kind of attacks we considered that I just didn't put the slides here because there are a lot of small experiments here and maybe it cannot be seen here quite clearly. So I'll just talk about them verbally. So those are alteration attacks. That means the objective here is just to change the IPDs, right? So in that attack, the attacker just tried to alter the IPDs. It didn't insert or delete packets, but it just tried to delay the packets at some nodes. So in this way, if we just make some unnecessary delays, in this way it will just say the like provenance content IPDs will not preserve, so that the at the base station it may get wrong in notion. So we also saw with the experiment results that it can actually resist various number of alteration, various percentage of IPD alterations there. Okay, and now I think this will just conclude the presentation. So in this paper, actually we introduced the problem of secure provenance transmission for data streams. There was no earlier work on this, so this is first extensive work on this, and we presented a watermark based solution that embeds provenance over the interpacket delays, and which also provides us several security schemes, security features that makes it survive against like confidentiality, integrity attacks, and also the experimental results support our claims. So our future work, like actually this was done a few times back. So later on, what we did with that, we used this scheme to detect packet dropping attacks for sensor networks, and also we tried to improve the granularity, because we said that showed that there may be LP plus 1 packet transmissions required to transmit the provenance. Afterwards, we also improved this granularity, that we just could transmit provenance for each packet along with it. So this is some also future works with this that was aimed for this work. So I think that concludes my presentation.
Okay, so are there questions from the audience? Okay, so if there are no questions, perhaps I can ask a question. So Salmin, this work focused on sensor networks, but can you also comment about which are the problems when you deal with the real, let's say, distributed systems, like provenance, capturing in operating systems, for example?
Actually, though I just talked about the provenance in sensor networks, we can easily adapt it to the data streams, for data streams where we see that there is nothing required rather than like some PN sequences. So that can be just assigned to some entities in the data streaming environments. But like as you said, for SensorNet, I mean, like while we talk about the capturing provenance in operating systems or some other distributed systems, the main problem here is that there will be a voluminous number of amount of provenance metadata that needs to be captured on in those environments. Here we just talked about the node IDs or PN sequences of each node, but if we want to capture a large number of information, then we have to have some kind of more robust mechanism there.
Can you mention some example of this information which can be captured at the operating system
Okay, so
level?
for operating system, so as we said that the data provenance for a data object just means how this data was, who generated this data and who processed and how it was processed. So in case of operating system, this data may be some file object or maybe some database tuple. So in those cases, you have to actually capture the actor who generated this data and what are the operations. Like for file object, there may be some create operation or sort operation that just generated this file. So those kind of information, and also the environment, like in which OS or which kernel this was happened, or maybe system configurations. There are a lot of things that may be needed based on your application of provenance. So that should.
Thank you. Are there other questions? If not, let's thank the speaker. Now, I repeat another time. Try to be on time. So from next time, I close the door after 10 minutes. And if you are not in,